What did we learn in our last session? LSTM stands for? Alright. What was the problem with RNN? What was the problem with RNN? Due to vanishing gradient descent, what was the problem?
Weights are vanishing. Weights are not updated.
There are no gates in RNN. Weights are not updated. So there is no learning in the initial layers of RNN, because of which it cannot hold or process or give correct prediction for longer sentences. है ना? So to overcome this issue, we came across another extended RNN model. What was that extended RNN model called as? LSTM, stands for long short term memory. So there were hidden states, same as recurrent neural network only, which helped you to calculate the next state output given previous hidden state and current input. Apart from that, what else is present inside an LSTM cell? What is present inside an LSTM cell? Input gate, output gate, a gate, and very important, cell state. What is the cell state like? It's like a long-term memory that is being provided throughout the LSTM model that helps you to retain important information out of the longer contextual text, longer text that you have given as an input, or longer sequential data, I should say, that you have given as an input and tries to predict output. So we have seen the architecture of LSTM, how it overcame limitations provided by RNN, right? And we have seen how these gates and cell state help it to retain a little bit longer memory and then give you good predictions with respect to sequential data, which is larger in nature. Okay, so now today we are going to see one of the exercise wherein we will try to design a model based upon LSTM. Okay, so what is this today's exercise? It is prediction of next word using LSTM. So it's my humble request to you, kindly understand each and every module properly, because tomorrow is your hands-on session for the same. If you understand today's session thoroughly, you will be able to perform good tomorrow when you do your hands-on exercise. Okay, so today's exercise here is prediction of the next word. So what do you understand by that? Given a few words inside a sentence, you will be trying to produce the next word that comes after the input that you have given. Okay. All right. So as we start, our first step, okay. So our first step here is to what? Import the prerequisite libraries that we are working with. So what are the libraries that we are working with? NumPy will be there. Now here you have longer range of sentences which you will be working as a data frame. So when you are working as a data frame, which library you would need? Pandas. Okay, so I am importing pandas, I am importing NumPy, I am importing PyTorch. I will be working with neural network models, so I am importing NN library out of PyTorch, and then I am also utilizing optimizers from it so as to I get a optimized version of the output using suitable optimizers like SGD, ADAM, whatever it is in your model. Okay, so the first step remains same, you are importing libraries. Now second is to create your data. Okay, so here you can do a number of things. Either you can import your CSV files, either you can import your text file, or you can create your own data set. Here I am trying to build my own data set. Okay, so what am I doing over here? I am creating an example data set. So for that I have to create a dictionary. So here I am creating a dictionary labeled as data, and then it contains key and value, but of course, so the key contains your text, which is having a list, the value has got a list of movie review strings as its value of that particular dictionary. So dictionary key is text and the value is the list of strings that is giving me reviews about the movie. You can give any type of data set. So it's a bigger paragraph that you can see. The first sentence, at least if you can remember, it will be important for me to trace out throughout the code. So what is the first sentence here? The movie was fantastic and very engaging. So if suppose whenever I am running my model, I give the movie was and it should be able to predict me fantastic. And if I give the movie was fantastic and very, so it should be able to predict for me engaging. Are you clear? So this first sentence, at least out of this data, you remember for throughout our explanation of the code. Clear enough, guys? So now, once I have created my data set, I have to create a data frame out of that particular data set that I have created. Okay, so using pandas, I will create my data frame, okay, and I am calling that data frame as DF. I am creating that data frame out of the data that I have just now created. Now, start with text pre-processing. So now all these steps that I am telling now here, I will be using important parts of pre-processing here, and this is like prerequisite steps before you create any sequential model. Rather it may be an RNN model, LSTM model, GRU model, or it can be before building a transformer also. So these are the common steps that I am teaching you today. Although I am building an LSTM model for sure, but all these steps remain common throughout. Okay, what is it? Text pre-processing. I mean, you have to understand one thing. You have been doing your machine learning programs, no? Yes or no? So, suppose if you want to go for a small scale sentiment analysis, you might have done. Hai So, what you had to do, if you want to build a particular, say, classification model or any regression model, for an example, you would like to give your data in the form of what to the model? What would you give? X and Y. Yes or no? Yes or no? You would give X and Y, set of inputs and then an output out of it. Correct or not? But now here what is the input, guys? Input is what? String. Input is string. So is it easily pre-processed by your machine now? Is it easily processed by your machine now? Can your machine understand it? It's a human language that you are giving as an input, no? Okay, so machine cannot understand it. So what is your aim now? Your first aim is to make your data into a format that is suitable by the machine to take it and get your model trained. Building a model is secondary. First we are trying to build our data suitable enough for the machine to learn from it. Clear enough? So now my aim as a layman language I am going to tell you today is, out of all these set of strings, I want to create my X and Y, if you really want to understand. So now I really want to understand X should be certain input that I am going to give and Y should be certain output that I am going to expect. And using these set of X and Y, first I will be training the model, later I will be providing X, I will be testing for Y. That is the process, no? You have been learning throughout your machine learning. Yes or no, guys? Yes or no? You give X and Y, you train your model, you evaluate your model based on giving X and predicting whether it is giving you correct Y or not. That's how you work. So that's how what we are going to, I'm trying to put it as simple as that for you people. Okay? So I'm taking this data which has got textual input. I want to convert it, make it suitable in the form of X and Y so as I can train my model once I build it. Clear enough? So that's my aim, the partial aim. Okay. So now, first step that comes under pre-processing. What are the several steps that I taught you so far in my last class? Tokenization, lower casing, lemmatization, stemming, stop loss stop words removal. So all these steps I have taught. All of them are not so important that you have to follow the sequence and go it throughout. But I said, when I was teaching you embedding layer, I said there are two most important steps. What are they? Tokenization and word embeddings. So I am going to use only those two steps here. You can go for lemmatization, you can go for stemming, you can go for stop words removal as per your requirement. Okay, you can. Already how to write those codes and all we have seen. Okay, now again one more important, guys. Again I am telling you, coming to the next exercises that you would be doing in your hands-on or here, it is not always necessary that you build your word embeddings from scratch. I've told you how to build them from scratch, but I've also told you, you can use pre-trained vectors models also. Hannah, can you give me one example for it? Very good. Word to vec, fast text, globe, etc., etc. So suppose you have been given a choice to use pre-trained vectors, it saves your time in your code. You need not write everything from scratch. Okay, but here I am choosing to create randomly generated vectors so that you understand what exactly is it. Okay, so just passing and getting the output we don't want right now. I'm just trying to build you a scratch code for it. Okay, but you can use freely use pre-trained vectors also. Okay, now, so the first step that I want to go while designing my embedding layer is tokenization. So here I begin with writing a method for tokenizing what I am passing as an input, text that I have generated, and see this particular instruction, it's a comprehension instruction. Many things are being done in that particular instruction if you pay attention. First, we have created a tokenized method. In that, I am using text dot split. So what is that text dot split? When I apply a dot split method to it, it splits that string that I am passing into a list of words wherever it comes across a space or a boundary automatically. The other day we tried to give everything, you know, we tried to define our boundaries and we then extracted words out of our text. Yeah, but today we are doing it automatically here by using dot string. Okay, so here I am applying dot split to my text, and then it helps me to segregate all my words out of my string text that I have given there. Now, for every word that I get after my splitting operation, for every word I am applying a dot lower method. So automatically what is happening? All my words that are generated out of that text, it is converted into lowercase. Why is it important for me to convert all these words that I have generated into lowercase? To avoid case sensitivity. Okay, so here in this instruction I am doing two things, automatically extracting all the words and then converting them into lower cases. And then where do I store them? I actually here return all these things, and then you can see I return it as a list. Okay, so now after I pass my text into the, you know, as an input to this tokenized method, it returns me a list wherein it has got all the words that are present in that string of text that I have passed, but in lowercase format. So I have tokenized my text, yes or no? Right. Now, here what I am doing, now I am applying. See, the steps are like this. We are creating a function, we will apply a function. Creating a function, applying a function. So the first function that I have created is for tokenization, called tokenize. Now I will choose my actual data set that I am working and I will apply that function. So what is the data that I am working on, guys? It's a data frame of movie reviews. So this data frame that I have created, I gave it the name as df text. Remember? So now this df text, I will use dot apply. What I am going to apply? Tokenize, that I have just now created. So to my data frame, which till now had only one column of text data that I created, I am applying tokenize. Okay, where it is getting stored? So now what is happening? My data frame will now have what? Two columns. Earlier column was text column, wherein everything was a normal string that was given to it, right? Right. Now what it will have as my another column is its another column, it will have tokens. What will the tokens column have? List of words that are present in the string separated, and they are also lowercase. Clear enough, guys? Yeah. So now I'll print this data frame after I apply the tokenize method. Can you see there? Right? So the first column, see, you can see the columns are placed one below another. Do not get confused, but they are like column wise, okay, because clearly their index is mentioned. So 0 to 5, I have got my text, that is my original input that I have given, and then the next column is about tokens, where you can see every string that is present in that data frame is converted as list of words, separated words. Okay, clear enough? So we have successfully tokenized our input. Okay, what should be your next step here ideally? What should be your next step ideally here? Lemmatization, stemming. If you want, you can go for stop words removal. But I said I am following up with some basic steps. My data is very small. So what I am going to do here is directly I will go for word embeddings. Okay. You can go for stemming and lemmatization again. I am not stopping you from that. Okay. Now, what is now my next strategy? To build a function which would create those word embeddings. Then we will see how do we apply that function. We created tokenizing, we applied tokenizing on our data frame. Now we will create word embeddings method and we will try to apply that method. So what is the name of the function that I have created here? It is create vocab and vectors. Chosen very carefully. What we are going to do now is, out of those tokens that is available to us, we are now building vocabulary for our model. Try to understand. Vocabulary for our model, what is it, ma'am? How different it is from tokens? So, machine vocabulary should be like, machine should have a key and a value to understand for a particular word that is coming as an input, what is its vector. The other day I explained you why that word vector is so important. Do you remember? Machine cannot understand strings, right? So you have to give a lookup table. You remember we created an embedded matrix. So that embedded matrix is very important for us to build and give it to the machine, to our model that we are building. Are you clear? So here we need to build our vocabulary. Vocabulary is nothing but our lookup table or our embedded matrix that is going to take word and it is going to map with what? Its word vector. So that we are going to build here, and that's how the chosen name here is create vocab and vectors. Correct? Now what are we passing as parameters here? Tokens underscore list, vector underscore size. Okay, so when I am giving this to my model, when I am applying this to my model, will I use the same token underscore list there? No, I'll give what are the tokens name that I have given just now. Okay, we will see that also. And then what is the second parameter, guys? I told you it is what type of parameter? Very good. It's a hyperparameter. Understand, what do you understand by that hyperparameter? It is going to indirectly affect the performance of your model. So here we are choosing it as 50. Based on your length of sequence, you can choose it to be 50 or 100. We will even understand why it is so important to choose this. Okay. So now, first thing that we have created here is a function wherein I have defined a function that takes a list of tokens and an optional vector size. By default, it is 50. If you want to change, you can change. Now, vector size is equal to 50, and now what I am doing here, I am building a vocabulary I told. What should be a vocabulary like? It should be a dictionary. So my first step would be to initialize my dictionary, which I am naming here as vocab. Okay. Now, what is happening here? There are two for loops here. What is it for? What is this iteration for? So first one is going to do what? It is going to iterate over each list of tokens inside your token list, and then over that, see, there are like data frame mein, you have got several rows which has got strings, and then inside that strings you have several words. So that's why you have to understand we are doing here iteration twice. Okay. Once what you have done, look at this particular thing. Why have I written this particular instruction there? Tokens, can it be repeated? No. Tokens have to be unique. Do you remember what method we used in our last exercise to give that uniqueness? Set method. So here what I am just doing is I am just going throughout and checking if there is any token that is repeated using this if function. I am not using a set method. Okay. So if token not in vocab means it should be a unique token. It should not be a repeated token. If it is not a repeated token, then what of course, what you will be taking it using a random function, you would be generating a vector and size you have already defined there as 50. Okay. You should actually, I am waiting for that question, why vector size is 50? Nobody is asking me that. Can you change it? Yes. What happens? Why? What should I take? Can I take it as big as possible? What is the advantage if I take it as big as possible? It is able to cover a large amount of data. It is able to, perform lot of, it will be able to work on longer sequences, cover longer sequences in its memory. Yeah, but then what would be the disadvantage? It will be slower in computation. What happens if I take it very small? Yes, it will not be able to remember that much. Okay, it is not able to give you an optimal performance out of it. So that is why it is a hyperparameter. Now you understand, you have to carefully choose it. See, even the learning rate that you have been learning so far, we don't take it randomly. We take it at a very, a range of say 0 to 0.1 maximum, just like that in between. And then you see whether learning is proper or not. So same goes here with the vector size. So here by default value is 50. So I am going with that. Okay. So now coming again, we have now successfully created a vector for every word that is coming into our text by using np.random.rand method with a parameter as how much size of vector that you would like to generate. Everybody, are you clear? So what did we do as our steps, guys? We first imported libraries. We then created our data. I am creating. You can use any data from text file, from CSV file, or you could generate your own data, sequential data. I have done that, okay, wherein I just converted that data into a data frame so that it's easily accessible, okay. It has got certain rows which has got some strings of text inside it. I tried to convert that into tokens using tokenize method. Now here in this method, I am trying to build a vocabulary. That is, I am trying to build my word embeddings throughout. So I scan through all the rows, inside every row, all the words, check if the token is not repeated, and then convert that into a fixed size vectors, wherein I am now creating my vocabulary. Okay, clear enough, guys? Now, here it is going to give me output as a dictionary which is containing the vocabulary and their corresponding vectors. Clear enough? So we built a vocabulary. Now we created that function. Now we will apply that function into our model. Yeah? So now what I am supposed to pass here, I am going to create now vocabulary for my model by passing my inputs that I have got in my data frame. I mean labeling whatever I have done it as per my input that is present. I pass it through the function that I just now created. So here I am passing what is my input. There my input is now data frame. Earlier it was data frame text, which I am not using now because I converted that into data frame tokens. Understanding? So what I am passing here as my input now, data frames of tokens. So all my list of tokens will now be given as an input, wherein now a vocabulary will be created out of it. It will have key as every word and a value as a corresponding word embedding or a vector that is associated with that particular word. Clear enough? Now you can ask me, can we stop? Because word is there. You got your vector. That's where we stopped our pre-processing exercise, na? Yes or no? No. From here, actually, it starts. That was just a trailer that you have seen in the last exercise. I'll still say that it is still vector. It is just a bunch of vectors. Yes, of course, they are numerical in nature. Yes, of course, your machine can now understand it, but still I will say the data is not sufficient enough for the machine to understand. Not machine to understand, data is not sufficient enough that I take and train the model just like that. Because to train a model, I have to train it telling, see, this is the input and then this is my output. Some list of input and output, train the model and then evaluate the model based on just giving input and test for output. Now is my data in that format? No. I just have got a dictionary lookup table telling this word has got that vector. Now, how do I train the machine? How do I tell the machine what is the need? So that means I have to still filter out my input. I have to still change it into the way that I can train a model. So here comes now the aim of my exercise. What is the aim of my exercise? Word prediction. So I have to first decide that, see, as a human, I can go with n number of length and I will try to predict. But I am making a machine train. I am giving that capability to a machine. Machine always comes with a limitation. I have to give certain instruction. So I will first set up an instruction to the machine. You have to predict a word, okay. But then how many words am I going to give you as an input? Okay. So first thing is like machine should be understanding at least say 3 to 4 words. What is the context of those 2 to 3 words, whatever you are fixing, and then try to predict. So you have to fix now size that it wants to take out of the input, try to find context or inherent relationship between those words and try to predict the output. Are you clear? So now we are going to build that particular strategy from here on. Okay, word embedding layer part is over, but still your input is not good enough to be able to train your model. You have to undergo further processing. So, okay, so this was now where we stopped at in pre-processing, right? Every word will now have a vector of dimension 50. So you can see the first vector was the, and then you could see an array of 50 elements. Then next was movie. There was an array of 50 elements. I told you, you can print and see that vector when I was teaching you the pre-processing exercise. So this is where we have stopped. Okay. Now, we have to still prepare our data set for word prediction that I told you, right? So again, you will create a function and then you will apply that function to your data set. So I am first creating a function that is making me prepare my particular data, enable it to be able to enable it so that I can choose words out of it, understand the context, try to predict the next word. So now my data should be now into that format that let's say if I choose 3 words, the 4th word should be the output. Yes or no? Because that's what is your word prediction. Hai na? So if I am giving say 3 words, the 4th word is my output. So now in that entire paragraph that you have given, you have to build your data in such a way that you have to slide through all 3 words and check what is the 4th word. So first 3 words should be your input, next word should be the output. Slide the window. Next 3 words should be the input, next one, 5th one should be your output. Slide the window like that. So till then you have to scan your entire sequence and then give it to a machine. Now this is your data set. Now this is your proper X. First 3 words X, Y is the 4th word. This is your training data. Train on it and then you try to predict when I evaluate the model. Are you clear, guys? So that's what we are going to do now. If you understand this strategy, code becomes easier. If you have got doubt, you can ask me here itself. Are you clear? You created embedding vector. Till here everything was clear as per last exercise. Now is my exercise demanding what? I have to give x and y to my machine or to my model. Okay, so I should slide in my sentences, pick up some words and check for the next word. Put that in output, take these say 3 or 4 words as my input. So for that first thing, I have to first measure how much should be that sliding window. How many words minimum that I am supposed to give to that model. This is again a hyperparameter. This is again user specific. Okay, how many words you want to give to the machine so that it take that as an input out of all the sequences, understand the context and then give you the prediction. Clear enough, guys? So now look at this particular thing. I am here creating a function called prepare sequences. What are the parameters that I am passing, guys? I am passing here 3 parameters. What are they? Tokens, the word that I am dealing with. Vocab. Vocab, why it is needed, guys? I built my vocabulary, no? Machine will not understand word, no? It will understand the vector associated with it. So I require my vocabulary that I just now built it. So I require my word, I require my vocabulary. What is the third parameter that has been passed there? Context size. What do you understand by context size? I just now told. If I am giving say a sentence of 10 words, I have to prepare and predict next 11th word out of it. But machine, you cannot dump a machine and say you scan through all these 10. You can, but then say for ease of computation if I fix it as 3. Okay, so suppose if I am writing that sentence, do you remember our first sentence out of our data set? The movie was fantastic and very, the movie was fantastic and very engaging. 7 words were there. है ना? So if I say the movie was fantastic and very. So how many words I am giving? 6 words I am typing as my input. It should be predicting me engaging. So out of these 6 words, to perform ease of computation, let me say I will take only the last 3 words. Why do you have to do? Why do you have to convert those context words into vectors? So that the machine understands. Okay, fair enough. You are converting it into numerical. Okay, fair enough. What are you doing to y dot append? Don't I have word in y? I have words in x. I converted that into. Don't I have a word in y? Why am I not converting it into vector? You should have asked me that question. Exactly. We are not performing any further calculations on output. We are just predicting the word and leaving it. So, index of that word is crucial for us to get back that word. We are not using it anywhere further for computation. So, that's why we are not converting that into vector and then again doing something out of it. It's over. That y is my output. I require only index out of it. So, it saves time and memory in my model. So, here what I am doing that because I require the prediction to be only the word that I need to extract out of the given data set, I require only index of that particular word and then I will show it as an output. Okay, that's the reason X is taken, their context words. It is taken and converted into its subsequent vectors by passing it through the vocabulary, by taking it from the vocabulary, but wherein Y is the output that I need, I am just taking its index which I will use for displaying the output. Clear enough, guys? So, this is one important thing that I wanted to tell. Now, later what I am going to do to make computations easier, I am going to convert that as NumPy arrays. Okay. So, now this particular function, prepare sequences, what it is doing? It is taking tokens What it is returning? X and Y. What is X? Context words. What is Y? Clear? Now this is properly pre-processing that we have done as per our model now. Given a paragraph, you try to convert that into tokens, and then after you have done with tokens, you converted them into a vocabulary wherein you did your word embeddings, you created vectors out of it. Then what did you do? Then what did you do? You created a context window and then you converted your tokens into context words and target value. And you are now generating a NumPy array out of it. Clear enough, guys? Yeah. Now we will apply the function that we have created. We just created it. We will now apply it to our data set. Okay. So now what am I doing? I am choosing my context size as 3. I am initializing my list. I'll go through my data frame tokens. That's the name that I have given for my particular data set. So data frame tokens, and I am going to call my function that I just built, prepare sequences, passing on tokens. Tokens is nothing but my data frame tokens. Vocabulary, whatever I have built, and context size here that I have chosen it as 3. Important part here, I am using here one more method. What is it? Could you tell me what is the difference? What is the difference between append and extend? You are already pro with Python, I guess. What is the difference between append and extend? What does an append function do? What does an extend function do? Is there any difference in the output that you get when you use both? No idea? Okay. We will see it. Okay? If we use append, okay? If we use append there in place of extend, it would add the entire list, which we are calling there as X sequence, as a single element in X. If we are using append, it will add that list as a single element. I'll show you one example also. Okay? But if you are using extend, it will add each element of X sequence to your X. That's why we are choosing extend. You can see one example. 2 lists I have taken there, 1, 2, 3, 4, 5. If I am appending, what is happening? 1, 2, 3 was there. If I am appending, 4, 5 list is appended just like a single element, which is which we don't want. We want elements of that second list also to be coming into the first list. For that reason, we have to choose extend. Clear enough? So that's the reason. Going back to my code, I am choosing here whatever sequences that I am getting after I have prepared my data, I am going to extend that to my X and Y. Everybody clear? What is the output of this particular thing? Obviously, the output is going to be 2 NumPy arrays. First one is named as X. What does X hold? X hold context words which are now represented into vector form. Okay. And what does Y hold? Y hold target word, which is nothing but the index of target word. Clear enough? Now very easily you have converted your entire sequential data into X and Y. Can I train a model now? Any model? Now the input is good enough that I can choose any model and start training with it. But then we have just done with input. We have to build our LSTM model so that it performs prediction. At least first part of your code is clear. How you are working with input? Yeah. I think we can skip this. I have explained you this. So this is what if you print X looks like. As I told you, X is a NumPy array, and then It is holding all the vectors that are relevant to your context words. Okay? Now, there are 3 words, so you can see that is holding 3 vectors of dimension 50 each. 3 brackets you can see, no? Yeah? Fine. And what is Y? Index of my target value. Clear enough? So I have printed X and I have printed Y for you. Now, very important. The next step is to convert data into tensors. Why? I already have it in a machine calculative format. I have got it in the form of NumPy arrays. Why do I require it to convert it into tensors? What is the advantage if I convert this data into tensor? What is tensor? What is a tensor? No idea? What is a tensor? You have been working with deep learning, no? So, a data, if it is represented as a tensor, it is nothing but a multidimensional array. Okay. You can store multidimensional array inside a tensor, and mathematically computations are very easy when you perform it with tensor A. Okay. The libraries that we have got, PyTorch, TensorFlow, whatever, they all work with tensor, because deep learning involves lot of heavy mathematical calculations. So working with tensor is very easier when compared to NumPy arrays for such heavy calculations. Okay, first thing is that. Second thing, here in our model we are converting it into tensor is because you can use it on any global platform. Okay, whenever you are choosing your model to work from one place to another place, that compatibility it is going to give, because most of your environments, they work with tensors. So if you have got your entire data to be converted into tensors, it's easy for you to relocate your program, and you know that compatibility, portability, it brings it to you. So 2 things. First is, but of course, yes, the computations are very smart and speed enough that I work with tensor. It is able to hold large amount of data, multi-dimensional data I can work with when I am choosing tensors. Are you clear? So here my next step would be to convert my X and Y into tensor by calling tensor method from torch. Now you can see very important difference here. What are we choosing as our data type? For X I am choosing it as, for Y I am choosing it as Y. What is X? Context word vectors. So obviously float 32. Yeah? 32 point operations. Okay. Y? Index. Index means integer. So long. 64-bit integer. Clear enough? As I explained you just now, why do I have to convert it to tensors? I am again telling advantages is you can perform, tensors actually support huge amount of computations on GPUs, which can significantly speed up your training and inference. So GPU acceleration is one advantage. Second is automatic calculations of differentiations or gradients is possible when you are working with tensors, PyTorch tensors, and it is very, very important part out of a neural network inside your back propagation. For every step you would be performing calculating the gradients. So easier and effective gradient calculation is performed, and compatibility, which I have already told you. So these are all the advantages when you convert your input into tensors, and that's why we are doing it. Now, coming to the second part. What is it? Building an LSTM model. Okay. So till now you were working on only on your input, trying to make it into a format suitable enough for the model to train. Now building a model. So what are we building? We are building an LSTM model. Okay. We are building a sequential model, LSTM model. So first we will define the LSTM model here for word prediction. For that I am creating a class called word prediction. Okay. Now, I'm defining a class here called word prediction LSTM, and this particular class defines LSTM based neural network for word prediction. There is this init method here. It is going to initialize me all the layers and the parameters that is present inside this particular model. Okay, you are clear enough with this, right? Now, what are the parameters of this init function? Self-instantiating, and then input size you are supposed to give to your model. Because you are working with an extended RNN model, there are hidden states inside it. You are already done your RNN modeling. So here also we are supposed to give my hidden state, input size, what it is going to deal with, hidden size, what is it going to deal with, and what is the vocabulary size that it is going to deal with. So all these three parameters you are going to pass on. Now, size of input features would be the size of word embeddings. So what is the size of word embeddings that we have got? What did we choose for our model? 50. And then hidden size, what is the size of hidden state in your LSTM that you choose to? Again, hidden size is user dependent. You have to remember, we have to give hidden size in the form of 2 power n, like 32, 64, 128, etc. Okay, again this will be user specific. So input size would be the size of your embeddings that you have chosen, that is 50 here in this model that we are doing. And what is the hidden state size? You can choose it to be 64 or 32 or 128, 2 power n format. And then what is the size of vocabulary or the number of unique words? So you have to calculate the length of your vocabulary that you have created and give it over here. Clear enough, guys? Now, you are now going to define what are the layers inside your model. So what is the first layer? See, it should be always like layer by layer. You can choose several layers of LSTM also based on the complexity of your model. My model here is very simple model, predicting the next word out of given 3 words. I think 1 layer of LSTM will be sufficient for me. So it's a very simple LSTM model. So here I am defining 1 layer of LSTM, self.lstm. So I am invoking an LSTM module out of it, wherein I have to pass my parameters. What are the parameters? Again, input size that I will be giving and hidden size that I will be giving. That third thing is very crucial, guys. What is it? Batch size equal to 2. Now that parameter, if you are giving batch size is equal to true, what effect it will have is, it will be affecting the dimensions of your inputs and outputs that are coming through your model. Why? See, we have built a smaller data of few lines, but sequential modeling actually works with, like, majorly all your real world NLP tasks, they work with huge corpuses of the data. You have got multiple lines that are coming and going. So what do you do there is, you pass on sentences as batches. Okay, all the sentences are clubbed as batch and then given for processing. So subsequently, the input dimension that you had will now have a prefix to it, which will be your batch number. So batch will also be one of the dimension of the input as well as the output. When would be that case? When you give here batch size is equal to, batch first is equal to true. Batch first. Batch will come as your first dimension, followed it up with whatever be your dimension of input and output. Are you clear here? Yeah? So here I am keeping batch first as true, so that the input and output tensors are of the shape batch size, comma, sequence length, comma, features. So that would be the dimension. 3-dimensional tensors now. Till now you had only 2 dimensions. Now it will be 3 dimensions. So this is also a requirement. Why from NumPy arrays you have to convert your inputs and outputs to tensors, because now once batch comes into picture, it becomes a 3-dimensional array, and tensors are easier to deal with in multi-dimensional array format. Are you clear? Right. Now, Next is what we are doing here. Obviously, follow it up with a fully connected layer. Fully connected layer will perform that linear transformation part of your neural network. Okay, here to keep it very simple, I am choosing only one layer. Depending on your application, you can choose one or two layers or more layers of LSTM. Okay, so here I am ending here my model by defining a linear layer, which is my fully connected layer, which is going to map my hidden size to my vocabulary size. Okay, now this layer will convert hidden state from LSTM to the predicted word. So basically, out of all the hidden states, see there are internal all hidden states, there are internal cell states. We don't need all of them here. What do we need? Only the last hidden state. So that last hidden state will help me to predict what is going to be output. Remaining all internal hidden states, cell states, what memory it is creating, what internal calculations LSTM is doing, I am not bothered here. I am only bothered on the last hidden state that my LSTM is producing for me. Clear enough, guys? So, have a look now. After I have defined my init function, I will now define another function called forward. So what it is going to do this forward function, it is going to take X as an input. X means context words you are giving as input. What it is doing there, it is applying an LSTM model to it. Just have a look, I'll break it down for you so that you understand. This is what we are writing in the context, we are writing in the forward method. Taking X as an input, X is nothing but your context words. What is happening here? So here, when I am applying an LSTM layer, it is taking X as an input. What is X now? X is not simply word embeddings, context vectors now. It is a batch of word embedding because we gave their batch first is equal to true. Okay, so X here is nothing but a batch of word embeddings which is passed through LSTM and it returns two output. The first, see, what are the two output you can see? You can see this particular piece of code. I am applying here LSTM to my X. What is in my output part? Two outputs are there. है ना? What is the first output? Underscore. Please relate to the code. Yes or no? What is my first output? Underscore. Comma. What is my second output? Tuple. It's a tuple. Tuple has got what inside it? Hidden, comma, underscore. So what is this underscore? Wherever you want to ignore any values, you will use underscore. So here, the first output here is not captured. We are ignoring it. We don't even want to know what is it. What exactly is it exactly? It is the output of LSTM at every time step. We are not bothered. We don't want to store it and waste our memory. So we are ignoring this computation. What is that? It is the internal outputs at every time step of your LSTM. What you require? Only the last hidden state. So that's what you are capturing inside that tuple. Giving hidden because what you require is the last hidden state. Yes. Then what is the other part of the tuple? Other part of the tuple is again ignored. We don't want. What is it? It is the cell state output. Understanding? So I am not taking it, I am not storing it just to save my memory. So I am ignoring what? I am ignoring all the internal outputs of my LSTM at every time steps. I am extracting hidden state. I am ignoring cell state. That's how underscore, comma, inside the tuple I am writing hidden because I want hidden state, comma, again an underscore because I want to ignore what is cell state output. So I am taking X, context words, I am applying LSTM layer to it. From the LSTM, I am only taking hidden state, ignoring every other output that I could actually get from it. Clear enough, guys? A very, very important part here. Okay, to extract the hidden states out of LSTM. So once it is done, what are you doing here? Try to understand hidden state. The shape of your hidden state will be like here, the number of layers, batch size, hidden size. So, number of layers, how many layers did I choose here guys? One LSTM layer, right? So, what should be my hidden that is coming as my output? What should be the size of my output? It should have one because that's a single layer that I have chosen, batch size and also the hidden size. So, again a 3-dimensional size that I am going to get here as an output. Now, what are you doing here? You are taking that hidden out of that LSTM layer and you are taking an output out of it. What do I want? Do I want all the hidden states? Which one do I want? Last. So, what am I doing there? I am writing hidden of -1. So, I am taking that hidden of -1 and applying it to my linear transformation. That is my linear layer or fully connected layer. Clear enough how things are going? And finally, at the end, what you receive is your output, that is your target value. So, out of those 3 context words that you gave as an input, you apply it to the LSTM layer. You don't want to take all the time steps, you put it as underscore. You want hidden states, so you write hidden there. You don't want cell states, so again another underscore. Out of all the hidden states that you have captured, you require only the last hidden step. That last hidden step is hidden -1. That you will be given to your fully connected layer to get you your target value. Clear enough how we are creating our model? Now, so what should be the output here? The output now will have a shape, batch size, comma, vocab size. Batch because we have kept batch first as true. Wherever you have kept batch first as true, you will always have a batch size first inside all the dimensions of your input and output. Now, coming back to our code, we created our class for word prediction. We created our LSTM layer and linear layer, and in the forward method we are actually applying those linear layer by extracting only hidden states out of our LSTM layer. Okay. Now we will try to initialize our model. Okay. So what are we doing? Input size is our vector size that we have already chosen it as 50, and then hidden size I am giving it as 64. Okay. And vocabulary size, as I told you, should be the length of your vocabulary for that LEN of vocab. Okay. And then you will be applying word prediction LSTM and storing that as my model. Okay. Once you are done, model is created. Now you have to train that particular model. For that, what do you require? You require loss functions to be calculated. Yes or no? You require to choose an optimizer to get an optimized value of your output. So, abhi that entire forward propagation and backward propagation will take place. There will be weights, there will be biases that will be automatically updated. Apart from that, all remaining things, you are aware what are happening. Okay. So, now you define a loss function. Here, it's like a multi-category classification. No, out of all the words, you are choosing one word as an output. So, it's like a multi-category classification. So, what is the loss function you will choose? Cross entropy. Okay. So, cross entropy loss and loss function you are using categorical cross entropy loss function. And then, what did I write there? To compare the predicted logits. What is this logit? What is this logit? Logit is nothing but raw data that is coming to me as my target value. Okay, target value is again a raw vector value that is coming to me. Still, I cannot say out of all the words or the raw vector that is coming, which one is my correct output. So, to know that, I have to figure it out into a probabilistic manner in the range of 0 to 1. Which activation function will do it for me? Softmax function. Okay. softmax function will figure out what is the probabilistic output in the range of 0 to 1. So that logit will be now given to a softmax function to understand within the range of 0 to 1 if this is your predicted correct word. See, it creates all logits for all the necessary words that could be. But you will pick up that word as an output which is having high amount of probability. So all these output logits that you are getting, you will have to pass through a softmax function to get the highest probability of what word is associated, and that word will be chosen as your output. So you will be defining a loss function as I just said, optimizer here Adam, and then feeding the batches of input. So here you can see one after another, I have got my loss function. See, how is my loss function given? It is taken as a name criterion here in this particular model. So criterion is nothing but I am applying my loss function, which is cross entropy loss function. Optimizer here is Adam optimizer. What does an optimizer do? It will update all the parameters of your model like weights and biases so that you get an optimized result. What is an Adam? Adam stands for adaptive moment estimation. Adam is a very popular optimizer in all neural network training because it takes all the benefits of stochastic gradient descent as well as RMS prop and build it into one. You have an automated momentum in Adam. So that is the reason it is very easier to work with learning rate there in Adam and coming to a conclusion at a very faster pace and with less losses. That is the reason we try to choose Adam optimizer more in building any neural network over there. Okay, so here also I am choosing Adam as my optimizer and storing its values inside a optimizer. Now, I completed this. Now coming to the training loop. Okay, training loop. You have fixed your loss function, you have fixed your optimizer. Now coming to the training loop, wherein you have to define how many number of epochs that you want to go through for your model. Here I have chosen it to be 30. Again, this is user specific. Number of epochs will also be dependent on how much, will also be affecting the performance of your model. The more number of epochs, you can get a decrease in the loss, but then overdoing it will again increase the loss. So you have to be having sensible value for epochs and keep a track. Okay. Next is, for those epochs, you will be training your model. You will be applying an optimizer here. Optimizer here is associated with a zero grad. What does a zero grad do? Resetting all the gradients, it will not be able to accumulate that gradient and save the memory space for you. Okay. And then after you apply optimizer, first comes is forward propagation or the forward pass, wherein you can see to the model I am giving X tensor. After I have created X and Y, I converted them into tensor, no? So that X tensor I am giving it to my model, I am trying to get outputs out of it. I'll take Y tensor and the outputs that I received from my model and apply it to criterion. Criterion, if you remember, there I am applying loss function. So it is going to predict me the losses over here. It is going to calculating the losses out of it. Now, once I have got that, I will apply a backward propagation to it, and then to the loss, I will apply a backward propagation, wherein gradients are used to adjust the weights and other parameters of your model. Once I have applied backward pass, I have to apply optimizer also, so that I get an optimum result out of it. So you can see here I am choosing optimizer. When I defined optimizer, I chose Adam. But then here optimizer dot step I am doing. So what is this dot step? What is the dot step here? Optimizer will update the model parameter in order to minimize the loss over here, okay, at every step. Okay. Now, you can see here, once I print my particular output, for every epoch, I could be able to capture here 25 epochs for you. So, for the first epoch, the loss was 3.4, and towards 25 it started decreasing, and at 25 it was 0.37, at 30th it was even more less. Okay, so you could see there is significant reduction in the loss as you increase the epochs. Now important, I am breaking down for that for you. I have to write my prediction function, guys. So what is exactly happening in this prediction function? Now I got my loss. I know that my model, what I have built, is correct enough. Now I want to start predicting. I have to see, given 3 words, is it going to predict me the 4th word or not? So for that I am writing this prediction function. Predict next word is the method that I am writing. Again, I will write first, then I will apply. So I am writing here, defining predict next word. What are the parameters? How many parameters, guys? 4. What are they? Context, model, vocab, context size equal to 3 by default. So what is this context? Context is the sentence that I will be typing. So as a user, I can type n number of words in my sentence. So that is going to be my context. Okay, but out of that context, how much is my model supposed to take? That is defined where? Context size. So context is what user is giving. Context size, how much model should take out of it. Apply it to the model that we have just built, LSTM model. And vocabulary, because we have to every time go for lookup table. Why? Context is given. User has written word. Machine has to take that key as a word, look for value in the vocabulary, convert that into vector and then process. So that's why 4 parameters: context, model, vocab, context size equal to 3. See, the user is giving again word, machine cannot understand that. So again it will tokenize that user sentence. Again it will convert that into vector and then process it. So for that reason, again you will do a tokenizing of what user have typed as an input. You will now here check if the user has typed sufficient enough, that is, it is equaling with your context size or more than your context size, but not less. Suppose if your context, the user have given as an input is less than the context size, you have to alert the user that you have to write a minimum of 3 words for the prediction. So that's what we are doing there. Raise a value error if the length of tokens that the user has given is less than the context size. There will be a value error. Otherwise, suppose it is possible that user can give 7 or 8 words, but context size is 3. So what are you going to take? The last 3 words. So what are we doing here? Tokens of minus context size colon. That means whatever tokens the user might have given, you have to take only equivalent to your context size that you have fixed. Here I have fixed it as 3. Clear enough, guys? Next, extract last words as equal to the context size. Now what you are doing? Convert these tokens into vectors so that the machine can understand. Now, convert the PyTorch tensors, convert these input tensors that you have, input vectors that you have chosen here as a context vector, you will convert that into tensors again. And then you will evaluate your model. Clear enough, guys? So now you got context, say, the movie was. If I write the movie, it should generate me a value error. It should tell me write minimum 3 words. The movie was, that I have given now. Suppose I have written the movie was very, it will take only movie was very. But then machine has taken movie as was very. It will not understand movie was very. So what it will do? Movie, comma, was, comma, very. Tokenize. Movie converted to vector, was converted to vector, very was converted to vector. Then tensors. Now those tensors will be taken and given to my model for evaluation. Clear enough? Now we are making prediction. With torch.nograd. What is this nograd? When I'm calling no grad, back propagation it will be very helpful because it will not track any gradients which we come across. So it saves your memory of your model. Now, with torch.noGrad, you apply that input tensor that I have just now extracted to my model and fetch me a output. Output is equal to model of that input tensor that I have given. Now, what are we getting as an output? Vector. What do you require? Index. Index of what? Output word. So, predicted index. You require a index out of that vector that has been predicted. So, you will use here torch.argmax. You will apply you will use torch.argmax and apply your output to it with a dimension equal to 1. That means it is going to, out of all the logits that were produced, all the words will be produced, but everything will be raw logit. You have to see what is the index of that, which word is going to be the output. So, highest logit it is going to take and predict the index of it. So, you will find the index of the word with the highest logit that have been occurred in the output in order to predict the next word. So, this dot item also I am using here to convert the index from the tensor to a Python integer. Okay. Now, so what you are doing now? Convert the index back to the word for display purpose. So, what you received was an index of the highest logit. Now, you look up in the vocabulary what is the index, what was the word associated with that index, and display that particular word. So, for that you will write here predicted word is equal to list of vocab.keys. In that you will search for the index that you have received, which has got maximum logit. Okay. Now you will return the predicted word. This particular instruction will convert the predicted index back to your corresponding word by accessing the vocabulary that you have built previously in the start. Okay. Now a testing function. It is not very crucial that you write a testing function, but writing an interactive testing function will attract your user. Okay. So what I am quickly passing through this interactive testing function wherein I will be printing enter a context sentence to predict the next word, and I have to, it is continuously giving you the output. So you have to write a code that when it should terminate, when it should stop. So for that I am writing, if the user doesn't wish to continue, he or she can type exit there. If he or she types exit there, then it will terminate the giving the output. Otherwise, it will continuously keeping on scanning the input that you are giving and tries to give the predictions. Okay. So here, enter a context sentence, and very first thing that you are going to check here is, very first thing that you are going to check for here is whether the user has typed exit. If it is exit, no need of model evaluations, you will simply terminate it. But if it has given something else, then you will have to start initializing your model and test it. So what are you doing? You are predicting next, you are calling predict next word that you have done, and wherein you are invoking your model with respect to your context, vocab and context size, and printing what is the output next word out of it. So this predict next word is called to predict the next word based on the context. Otherwise, suppose if the user has typed less number of words than your context size, it will generate you an error. Okay. So this is how your portal looks like, your interactive predicting method that you have written. So interactive word prediction, enter a context sentence to predict the next word, type exit to quit. So here we begin typing. So suppose here I have typed only two words, the movie. So it has generated me an error. Context must have at least 3 words, ensure the context has at least 3 words. So I'll rewrite again. And I wrote here, the movie was. So what is the predicted next word? Fantastic. Correct or not? Yes. Now suppose I give a very large sentence. The movie was fantastic and very. What is my context size now? 3. But I have given more better. More number of words than my context. Then what is it? Is it predicting for me? Yes or no? So it has taken only the last 3 words and it has predicted me a model. So that's how your model is working. Suppose if I press exit there, if I type exit there, then it is displaying me a message, exiting interactive testing, goodbye. Okay, actually speaking, till your loss function is minimized, that's the best way to build your model. But then here we are interactively predicting the words. So this is again user specific. Okay, so I think you are clear enough with the exercise for today. The major part went away in converting that data set into a format which is input output pair format, which was able for which would enable your machine to train. So you converted that into X and Y, then you built an LSTM model, then you applied an LSTM model, LSTM layer inside it and a linear layer inside it. You learned a very important topic on batch size, how batch is affecting the dimension of your input and output, and then you are predicting your model with the next word. In tomorrow's class, you will be doing a hands-on on a similar note with sentiment analysis. Similar note, almost similar. Okay, but you will be working with sentiment analysis. Okay, clear enough guys? So quickly take a break of 10 minutes sharp. Within 10 minutes, I'll start the quiz and then we have to start with attention mechanism. As I told in the beginning, it is going to be a big class, but you will not regret. You will learn so many good things about your next future exercises. Okay, take a break of 10 minutes and be back. Attention mechanism. So pay attention. You were doing your something and I just said pay attention. What did you do? You concentrated. So attention is nothing but concentrating. Okay, so attention mechanism we are going to see today. Now, before I actually dive into attention mechanism, I want to teach you on what is a sequence to sequence model. Okay, you have seen basic neural networks, ANN, CNN, RNN. Yeah? Now, in RNN, you have seen extended RNN, LSTM. Okay, today we are going to see very briefly about sequence to sequence. So, sequence to sequence modeling, I am going to teach you till that extent where it is relevant to attention mechanism. Okay, more on sequence to sequence modeling, you will be learning it as in then we go far with transformers and every other topic. So, today I will be teaching you sequence to sequence model pertaining to attention mechanism. Okay, so sequence to sequence model, they are also a type of neural network architecture which are used for transforming one sequence into another. So, what do you understand? You take one sequence and transform it into another sequence. This will be like a typical example of a language translator. Okay, wherein I say, hi, I am Priyanka and the language translator will say, Namaste, मैं Priyanka हूँ. So, I am going to translate from one language to another language. First one is also a sequence. I am going to map and produce another sequence which is having same context but in a different other language altogether. Are you clear enough? So, that is nothing but a sequence to sequence model example that I just taught. Okay. So, sequence to sequence model again is a type of neural network architecture which is used for transforming one sequence into another, such as translating a sentence from one language to another language. Okay. So, where you will be using all these sequence to sequence models, you will be using it in several applications like machine language translation. I just gave you an example. Hi, I am Priyanka. See all your Google translations. You just type one sentence and automatically it tries to give you the answer into any of your regional languages of your choice. है ना? So that is a machine translation model. Machine translation model is again a type of transforming model or a sequence to sequence model only. Okay, and you will also be using this in text summarization. What is this text summarization? I gave you this very good example now. Last minute before batting, you give one file to ChatGPT and you say extract a summary out of it, and then you read all the summaries, है ना? So entire thing, if you don't have a patience and you want to get a gist of the information that is being provided to you, you go for a text summarization model. That also uses sequence to sequence modeling, and also the very popular chatbots. Okay, so you give them a sequence of queries, you give them a sequence of sentence as your query, it tries to understand it and give you the answer in another sequence of sentences solving your query. Yes or no? So that is also a sequence to sequence model. A few examples to help you understand why do we have to study sequence to sequence model. Now, going into technicality, a block diagram of sequence to sequence model exactly looks like that over there onto your screen. So what do you think are the integral elements of your sequence to sequence model? What are they? Read. What are the important components of a sequence to sequence model? Encoder, decoder, and a context vector. So what is a context vector? Today in your exercise I made you understand. What is a context vector? Okay, so what are we trying to do here is, using an encoder, taking the input, we are generating a context vector. Okay, and the decoder takes this context vector and gives you the output. Let me help you put it into simple terms. Take the example of language translation. Hi, I am Priyanka. That is taken as an input by the encoder. It summarizes everything. The entire sequence will be compressed and summarized into one context vector which contains information about that sequence. So the encoder work is to get a context vector, getting all the context of what was there inside those sequences of sentences as I just told. Okay, hi, I am Priyanka. That context gets stored, compressed and gets stored inside a context vector. That context vector will be taken by the decoder, decompress, extract information out of it and gives the, natural language translated output. Namaste, main Priyanka hu. Understood? So that's what is happening. Encoder is creating a context vector. Decoder is using that context vector to give you the output. Fair enough? Now, so the sequence to sequence model consists of encoder, wherein the encoder processes the input sequence, compresses it into a fixed sized context vector. It typically consists of recurrent neural network layers like RNN, LSTM or GRU, because typically here you are working with sequential data, and it will encode the information from the input sequence step by step. Clear enough? Now, once you have done that, what it extracts for you? A context vector. So what does a context vector mean? It is a single vector which is going to summarize the entire sentence given at your input. Fair enough, right? And then this vector is passed from encoder to decoder. And then finally, what is happening at the decoder? It is going to generate you a sequence which is your output, and then from your context vector it is going to extract your output. Similar to the encoder, again it is a neural network which is having again recurrent layers only, because naturally it is also working with sequential data. So recurrent neural networks like RNN and LSTMs will be used in the encoder side also. It will also be used into the decoder side also. On the encoder side, to produce context vector out of the input sequences. On the decoder side, to use this context vector and produce you the output. Clear enough? Yeah. Now, What are the issues? Why exactly are we studying now attention mechanisms? So I told you I'm not diving much into sequence to sequence model. Just basic understanding is required because I am teaching today attention mechanism. So at least basics of sequence to sequence model is okay, right? Encoder, decoder, what does an encoder do? What does a decoder do? They are all neural networks only. Now, there are some problems that we are facing in this sequence to sequence model. What are the issues that we are facing? The first is this neural network is going to be quite deeper with an increase in the data if it is, and of course it is going to be harder to train. Okay, this particular model is going to be harder to train because for the recurrent neural network, if the longer the sequence is, the deeper will be the network in its time dimension and more time will be needed to predict your outputs. Okay, now second, also you have vanishing gradient descent problem lying, right? If you are using an RNN, obviously vanishing gradient descent problem is very, very common. But what if I choose LSTM, you can ask. So LSTM also has got its own limitation. Okay, first thing is even more huge, you know, in our real time today that we are not dealing with smaller data sets, we are dealing with humongous amount of sequential data. So there also LSTM becomes very slow. Why? The reason pertaining it calculates all the hidden time steps sequentially, one word after another. So imagine the entire corpus to be scanned. Huh? So it is going to be eventually taking lot of time, and of course vanishing gradient descent for that large amount of corpus also it will affect for sure. Okay, because you know we are keeping only particular keywords, not the entire corpus, and also everything is done sequentially. There is no parallelism, there is no concurrency while we are working with LSTMs also. Okay, so that was one of the issue, time consuming. So there is one more problem also, that is a bottleneck problem. So what is happening in a bottleneck problem? Bottleneck problem refers to the issue where the entire input sequence need to be compressed into a single fixed sized context vector. So imagine if the corpus is very big. It is difficult to extract the entire information into a fixed size context vector. So this context vector obviously will be used by decoder to generate the output. So output will not be that accurate. So all these issues were a part of a sequence to sequence model. Obviously difficulty with long sequences gave to bottleneck issue which I just told you, and it is particularly pronounced with long input sequences. As your input is increasing, there will be more problem with the, we call it as a bottleneck issue. Okay. Now, this particular model will be struggling to retain all that memory, all that input sequence, and then use all the relevant information from the beginning towards the end of the sequence. Okay. So, what is the solution to this particular issues? It is nothing but attention mechanism. Okay. Attention mechanism. I'll go back to this particular slide. Suppose two of your classmates are talking there where I am teaching. Okay, I just raise them up and I ask, see what I am teaching. So very quickly, as we humans are, you just look onto the slide. Are slide mein there's so many sequences. Is there something into, you know, something that is catching my eye? What is catching my eye? Bold letters. है ना? So, oh ma'am, you are talking about vanishing gradient, LSTM, bottleneck problem in a sequence to sequence model. You gave me correct output. Did you go through the entire sequence, guys? What did you do? You just captured your attention and picked up the key points and gave me the correct output. So that's the beauty of a human brain. We have a conscious attention and an unconscious attention. है ना? So the moment you look at something, you don't even look at consciously, but also it grabs your attention. Yes or no? But machine, no. So now what you want to do is, you want to impart that beauty of attention to your machine through attention mechanism. Are you clear? Okay. So solution is this attention mechanism. So attention mechanism, I am going to explain you in very simple layman language. So we all are humans, we are born with this exceptional beauty of capturing the attention either consciously or unconsciously. If I see a picture, I will not see it from the topmost corner of it. I'll just see it randomly somewhere where it catches my attention. Yes or no? For an example, see this picture. Okay, left one is a picture. I can see it in a different way. The right one, I will say, oh, I will not see anything. I'll say, why is this blurred? You know, immediately that thought comes. So, you are not going through that sequentially. Immediately, what catches my attention, guys? Oh, why is this blurred? I mean, somewhere in the middle, it is catching my attention. So, we as a human, we have a conscious attention as well as an unconscious attention. Are you clear? So, we would like our neural networks also to model the behavior of our conscious attention. So what is happening in our conscious attention? You just go through it, check the pattern between all those important keywords and give me the output. So that part I want inside my machine. I want to create that attention mechanism inside my machine. Now this is done by attention, commonly known as attention mechanism, wherein we are blurring out less important features and concentrating more on features which require attention to get the output. Clear enough with attention mechanism, guys? Yeah. So, what are the applications? Why you should understand this attention mechanism? Consciously or unconsciously, in your day-to-day life, you are using lot of applications which are based on attention mechanism. Attention mechanism not only is helpful in working with sequential data, it is also helpful, it is not only useful in the field of NLP, wherein you are working with sequential data, it is also helpful in the field of computer vision also. There are some of the applications that I have listed over there, like image caption generation. Looking at the image, you will be generating a caption out of it. That is possible when the machine gives an attention to that particular image. Image-based analysis, action recognition, text classification. Now that I am concentrating more here because I am teaching you NLP. So, text classification, okay, machine translation, speech recognition, recommendation system. Abhi recommendation system, what is it? Like, when I type something for searching, like say a fancy kurta set, all my relevant next ads will be based on that. So that's a recommendation system. It tries to give attention to what I am asking and starts giving recommendation. Same is happening when you are searching for some online shopping on Google or Amazon. It searches for pays attention to what you have typed and gives you with some recommendations. So everywhere in your day-to-day life, consciously or unconsciously, you are using attention mechanism. Today we are going to see how do we build it. First we are going to see what it is. In our next class, we will see how do we build it. Okay, now, coming to technicality, attention mechanism. Attention mechanism is crucial in many modern neural network architecture, especially in the task involving sequences like NLP and computer vision. Its primary function is to allow the model to dynamically focus on different parts of input sequence while processing the output sequence. There, this word dynamically is very important. We are not trying to focus onto our input sequence one after another sequentially that we have been doing throughout till LSTM. Till LSTM everything, HT minus 1 given to HT to get HT plus 1. To the current cell, you take the previous one and you try to find out the output out of it. We are not doing that. Here, dynamically, we are trying to focus and get the output. That means you are not scanning everything sequentially. There is a concurrency involved. There is parallelism that is involved. So, you are tracing, you are scanning through your input sequence in such a way that wherever it is important, catch hold of it and get an output. Not necessary one after another. So that's the beauty of attention mechanism. Very important. Guys, I am telling you, try to understand these concepts. In a very simple language, I am going to explain you this. Okay? So attention mechanism, actually if you go to anywhere, you will actually start by learning its types. but I am giving you a very different genre wherein you will understand what is attention mechanism in a very, very simpler manner, and based on that we will dive into technicalities, that is the types of attention. So kindly pay attention. So there are some components, key components that we call, that are involved in attention mechanism. They are called as Q, K and V. Okay? Q stands for query, K stands for key, V stands for value. So what is this Q? Q is the word for which we are making the prediction. K is the key representing each word or token in the input sequence. V is the value representing the associated information. Now, attention mechanism. There are these set of tokens that I have got. Where am I supposed to focus on? Where does my attention should go one after another word? How do I determine? Because I am telling sequentially I am not going to do. So there is nothing like t minus 2, t minus 1, t plus 1, nothing like that. One after another I have to jump to the words. Then where do I jump? I jump to a word which has more attention. How do I determine that? So there has to be certain process. So we call it as determining attention weights of your input sequence. Given any sequence of input, you have to determine attention weights. That is your aim for attention mechanism. If you get attention weights, means what? Every word in your input sequence will have an attention weight. Which one is given priority? Which has got higher attention weight. So we are going to see how do we extract attention weights through attention mechanism. Okay? For that you require three components, Q, K and V. Query is the word that I am calculating attention weight for. Okay? Query is current word that I need to calculate attention score or attention weight for. Key is all the words that are present inside my input sequence. Tokens, all the tokens that are present inside my input sequence. V is value associated with them. Clear enough? Value associated matlab wherever I am telling value, it means I am calling the word embedding. Remember that. Word embedding, vector. Because machine will understand that, no? Okay, let's see the analogy. Q. What is the next word in this sentence? K. Each word in the sentence tries to provide the answer. I am the next word. I am the next word. But how would you do? You have to find out a way which word should be given next attention, for which you have to calculate attention scores and attention weights. Okay. V is the actual representation that provides the relevant information. Let's see an example. The dog barked loudly. Okay. So there are how many words here? 4 words. Query. Suppose the current word that was supposed to be predicted is barked. Okay. So keys are what? All the words. What are they? The dog barked loudly. Value will be the word embeddings of each word representing the information the model uses. Now, the query, that is the word to be predicted, barked, the query will be comparing it with all the key vectors. Query vector will be compared with all the key vectors. Here comes the role of correlations. Here comes the role of similarities. Here comes the role of dot products. You all are aware, na? Dot products help you to find out similarity between two vectors. So here comes the role of these small mathematical applications that will try to tell you how well are these query vector and key vector related to each other. Understanding? Okay. So based on the similarity, attention score will be computed and values will be weighted. So you will extract attention weights for your values. Attention mechanism, the working that we are going to see. So in the simplest term, attention mechanism works by calculating weighted sum. This weighted sum tells the model about the importance of the features. Process of calculating these weights is crucial It may be different for several applications. Here I am explaining you this attention mechanism working in a very general sense. If you understand it, you can understand any type of attention. Okay? Now, what are we doing here is, the working of attention mechanism is divided into two parts here. The first part calculates attention distribution from the input, and second part calculates context vector. Try to understand here, in a sequence to sequence model now, I am now building only an encoder. I am using attention mechanism and building an encoder. Hai na? So encoder will take what? Input sequence, produces you a context vector. Here I am trying to produce context vector using attention mechanism. That only we will see. What about decoder part, ma'am? That you will learn in our upcoming sessions where we will be teaching you transformers. So complete model building you will be understanding when you will understand transformer. Our role for attention mechanism right now here for these sessions is try to understand attention mechanism with an encoder, wherein you will be generating your context vector. Clear enough, guys? Aim is clear? Now, calculating the attention distribution from the input means calculating weight of attention from the input, which input to be given what attention weightage, and then from there you will be extracting a context vector. That's our aim. Now, attention distribution is what we gives weightage to different inputs. Before calculating, the first thing that you have to do is encode your inputs using a neural network. So this encoded representation of input is called as keys. Okay? And another thing to calculate attention distribution is a query. What is query? What is key? I already told you. Query is the word that you are working on. Key is a set, is like all the words that are present inside your input sequence. Okay, and value is the associated value that it is holding, associated embedding value that it is holding. Now, a neural network computes, see everything is a neural network here, even attention mechanism is like a neural network. What does it compute? It computes correlation between the key and the query by some mathematical function. We are calling that mathematical function here as a score function f. So, this score function will take key and query and try to give you a score out of it, attention score, sometimes also known as energy score. Both are one and the same. So, you are taking query, you are taking key, trying to find similarity between them by applying some sort of mathematical function. When I teach you types of attention, I will also teach you what type of mathematical formula do you use for each of them. So, you are taking key, you are taking query, applying some mathematical function to get an attention score. Okay, you got the attention score. Once you got the attention score, okay, before going to attention score, how are you getting attention score? By applying some mathematical function. What could be that mathematical function? It could either be addition, it could either be it could be multiplication, dot product. So, it is type additive attention and multiplicative attention. I am not diving much into detail because today I am teaching you types of attention also. Therein I will give you entire formula itself, how attention is getting calculated. So, basically it involves additive attentions and multiplicative attentions, and some of these score functions incorporate learnable parameters, means weights and biases. You can also be using weights and biases in this particular formula of attention score calculation and calculate the attention score. So, that is how this mechanism works. Once you have got this score function using these, see these are some example score functions that I have shown over there. Can you see the learnable parameters like weights and biases along with key and query? You are performing here addition. So, this is an additive attention. You are performing here multiplication. It is a multiplicative attention and so on. We will see this in detail. Okay, next, coming to attention weights. So, you have taken key, you have taken query, you have taken weights and biases also in some places, in some sort of attentions. On that you applied some mathematical functions like additive attention or multiplicative attentions. Okay, what is the result? Is a score, right? What type of score? It is called as energy score or an attention score. But score, is that what you need? No. You require distribution of weights for your input for that attention. You require attention weights. So how do I get that? You have to apply a distribution function onto this attention score. Okay, so distributive function is again a mathematical function that you will apply onto this attention score. Therein you will get a context vector after you use this distribution. Okay, so the aim is get an attention score, get a distribution of weight, from the distribution of weight extract the context vector. So how context vector is getting extracted, you have to understand. First, what we are doing, attention itself is again a neural network. It will take the sequence of input, uses query, uses key, uses value, takes query and key, apply a score function, gives you an attention score. That attention score is taken, applied a distribution function to give you distribution of attention weights towards your input sequence, takes that distribution, applies value to it and gives you a context vector. Clear enough? So that strategy that I told you of the encoder, okay, taking input sequences, applying attention mechanism, getting a context vector. Are you clear enough, guys? So what is happening now? After you have got the distribution of attention, you will calculate the context vector. Before that, it is important that you should have embedding vector of every key. So that we call here as values. So you will have to call values also, and then context vector will be calculated as some mathematical function, basically weighted sum operation. Here it is represented as a mathematical function called phi. It is taking alpha. What was alpha? Weight distribution. And what is V? The values associated with every input sequence. So every input sequence and its attention weight, all of them will be added together and you are creating a summary for your encoder output. That is your context vector. Clear enough? So this is how an attention mechanism works. I am taking key, I am taking query, applying a mathematical function which could be a multiplication dot product for an example, and it gives me an attention score. It will be applied to a distribution function. It gives me attention weights. Attention weights will be linearly transformed with the values. Weighted sum output you will get as a context vector. Clear enough? Right? Now, in a nutshell, attention mechanism computes set of attention weights that determine the importance of different parts of the input sequence for generating the output token. Here nowhere we are working with t minus 1, t plus 1. So there is no sequentiality. Everything is based upon the attention weights that are calculated using query and key. Okay. Now, these weights are used to create a weighted sum of input features which forms a dynamic context vector for each decoding step. Clear enough, guys? Now, what is the summary of steps that we did? Calculate attention scores by using suitable mathematical function, calculate attention weights, weighted sum of inputs, and then generate an output. I have already briefed you on this slide. Different types of attention mechanism. So different types will come from the strategy that you are using in that attention. For an example, to calculate the attention score, if you are using addition, then you will go for this particular type of attention. We call it as additive attention or Badenau attention. Okay, it was introduced in the year 2014 and it computes attention score by combining the hidden states and in the encoder and the decoder using feed-forward network. Apart from addition of these hidden states, linear combination of these hidden states, it will also use activation function like tan h. Okay, mathematical formula is given here. Okay, this was the very first type, additive attention. Second is multiplicative attention. In that its variation is a dot product attention, wherein you can see here hidden state is getting multiplied here. Okay. And then in the end, you are doing this under root decay. What is this under root decay? You are doing scaling. You are doing normalization. That means you are dividing it with the square root of the dimension. Why? Because in mathematical calculations, if you are not doing normalization, the values explode. So to avoid that, we do scaling. Okay. So here this is scaled dot product attention. This particular thing is widely used in all NLP tasks, wherein you are scaling the dot product of, it calculates the attention scores by taking dot product of HI, that is encoder hidden state as well as the decoder hidden states. This is also one type of mechanism. Next is single-headed attention. Single-headed attention means you are using only one set of query, key and value. If you are using multiple, it is multi-headed attention. If you are using only one set of query, key and value, it is a single-headed attention. This will be enough for any simple task to do, but then if you have a complex relationship between various other words, you cannot go for a single-headed attention. You have to go for multi-headed attention. Self-attention, very important. Based on this, we will be doing our exercises. So, self-attention is where your K, Q and V come into picture. Okay. If you are using, single set of these query, key and value, it is single-headed self-attention. Understanding? So, self-attention means what is happening here is, it allows the model to relate different position of single sequence to compute its representation. Each token in the sequence will check or will relate to all the other tokens in the same sequence. Here you are not doing anything relevant to encoder and decoder separately that you have been seeing in the dot product. Here you will correlate amongst individual words in the sequence of your input only. That's why the name is self-attention. So, it enables parallelization and captures long-range dependencies. The formula is important, guys. Self-attention, attention score formula. Score function is Q dot KT. Why it has to be transformed? Because they are all vectors, no? When you are performing multiplication, it has to be done in that way. है ना? So, query into key transformed by again under root decay. Square root of its dimension. Why? Not to explode the limits over there. Scaling is important feature here. Okay. So, basically you are multiplying query and key, not multiplying, you are trying to find out similarity through dot products of query and key and also scaling it with under root decay over there. Okay. So, this is what you are doing there. Each token attends to all other tokens within same sequence. Okay. So, where do you use such type of attention, self-attention? Self-attention is useful in your chat GPTs, transformers like BERT. Okay. So, there are several things that you will be learning about in transformers which will be using attention mechanism. Self-attention is important. You will also learn multi-headed attention in detail when you will be learning your transformers. So, I am not diving much into multi-headed attention right away. For your information, I am telling like when you are using multiple sets of query, key and value, it is called as a multi-headed attention, and that's the formula of you. You will have an attention function wherein you will have multiple sets of query, key and value working with. Where would you use multi-headed attention? It is a very important component of building a transformer architecture. So, when you will be learning transformers in your coming sessions, you will be learning more about this type of attention.
Right now for us, self-attention is very important for us to understand the next exercise that comes into our session. So, what is this process of self-attention? Each word in the sequence is compared with all the other words of the same sequence, including itself. That's why the name is self-attention. Okay. So, the key idea is that Each token computes attention scores with respect to every other token in the input sequence. This is not at all similar to your RNN or LSTM where everything was updated sequentially. Okay, here we are not updating everything sequentially. Concurrency is achieved. Now, see the example sentence over here. The cat sat on the mat. First, we will tokenize it into the set of tokens. The cat sat on the mat, and we will embed it into its vector. Word embedding is done over there. And you can see here, suppose I am representing them into vector size 3.
So the cat sat on the mat is represented in the form of its word embedding. Sample I am showing. So for each token, now we will create 3 separate vectors. What are they? Query, key and value. These vectors are typically created by multiplying the token embeddings by learned weight matrices. Okay. So I already explained you what is a query. Query represents the current word that you are talking about and it asks for what to look for after the other words. I mean, suppose I am talking on cat. What is the next important word that I can go for? I should search for the next important word as per the distribution of attention weights. So that's why we are calculating attention weights for each and every token there. Understanding this? So key represent all the words in the sequence and act as a reference point for comparison. Value will contain the actual information that is associated with that token. So in this self-attention, for each word, the query vector will be compared with all the key vectors. And the similarity between query and key will determine how much attention should be given to that token's value. Whether this particular word is important to take into my attention or not, or should I go for the next important word. Are you understanding? That's how attention mechanism works. How do you calculate attention score here in self-attention? By calculating the dot product between the query and the key value. This measures how much focus or an attention a word should have on the other words. So the result is again a vector of attention scores. So for the example that we have taken there, the cat sat on the mat. The first word is the. So the became my query. The became my query. And what are all my keys? The cat sat on the mat. Those are all key vectors. What is my query vector? The. So now I will try to find out dot product between the and the. Query is also the, key is also the. Then query is the, key is cat. Query is the, key is sat. Are you understanding? So for all these you will try to calculate the attention scores. So this is the process. You take the query, you take the key, you apply multiplication over there, dot product, you scale it and then what do? Out of all the attention squares, which one has got more attention score? Which one has got more distribution? Distribution when I come, it means it is having a certain range of probability. So get an answer out of it, you apply a softmax activation function to get which one of them has got a highest probability of coming next in the attention. For an example, after the next is cat. After cat, the next attention will go on sat. On and the will not have much attention. The next attention will go on mat. So by visualizing you can say what is the importance here? Cat sat mat. That means you could interpret out of it the cat was sitting on a mat. Are you understanding this? So that's how attention scores will be calculated. One important word after another will be calculated based on attention scores, attention weights and their distributions. Okay. So I told you again, scaling is a very important process here. If the vectors are high dimensional, dot product will take a very large value and it will become an unstable model. That is the reason you have to square it, you have to scale it by dividing the dot product with an under root dk, where dk is your dimension of key vector. key vector dimension. Okay, and this scaling will help you to stabilize your model. Your model will not be unstable. So again, I told you, once your scores are computed, you will use softmax function to normalize them and bring it into the range of 0 to 1. And these attention weights will indicate how much focus or degree that you should keep on that particular word. For an example, if that attention weight is coming across say 0.9, that means you have to focus on that particular word. If it is coming like 0.01, that means it is of least significance. You need not pay attention to this word and you can go for next word that is coming into your attention. Okay. Weighted sum. Now how do you get an output here? Weighted sum of our values. So once you get your attention scores or attention weights, as I say, after your attention score, you cannot keep quiet over there. You go back to this. Here what we are doing, once you get your attention scores from softmax function, what are you doing there? You are again multiplying it with your value, because that's where your entire information is stored as word embedding. So once you get your attention score, it is important that you get a weighted sum of that. That is, multiply your attention score with the value. Obviously, no distribution of attention weight you got. You multiply it with the respective values that you have got in your vocabulary. So this vector has got this weight, this vector has got this weight, and finally, when you add all of them, you will come with a summarized context vector, eventually giving more weight to the word that requires more attention. The cat sat on the mat में the का value will be multiplied with least attention. Cat का value, the embedding vector will be multiplied with more attention score. Sat will be multiplied with more attention score, more weight. Obviously, attention weight is more. And then on the least attention score. And then again mat, a pretty good attention score. So when you multiply these values with these attention weights and add them, what you result? Cat sat mat. Understanding? So this cat sat mat ka numerical thing is your context vector that you are getting. Are you understanding how self-attention is now working? So this self-attention exercise, we'll be doing it in our next class. And where are you using such type of attention? You are using pretty extensively in NLP. Famous models that are using are GPT, your chat GPT, okay, and show, attend and tell models, vision transformers, all of them use self-attention inside it. So today you learnt about what is attention mechanism, why was it important, okay, basic strategy and entire attention process, how do you calculate attention score by applying suitable mathematical function, what mathematical function you are using will determine what type of attention that you are choosing. Also, how many set of QKV you are using also determine what type of attention it is, single-headed, multi-headed. Okay, self-attention is what is our key criteria here. I explained you about query, key and value. What is the algorithm that it is taking, how it is giving you context vectors out of it. So this part, if you are well, then next exercise we'll try to take input sequence, we'll try to generate a context vector. You will extend this mechanism once you start with transformers. Are you clear for today? Yeah. Okay. So that's it for today's session. Thank you guys.